In our video today, we are going to look at the direct comparison test as yet another test that we can use to determine convergence or divergence of an infinite series. Now, when we're using a comparison test, the idea is that we have a series of interests, which we're going to call A sub n, typically the notation that we use for an infinite series. And what we're going to do is compare that series, which we don't know if it converges or diverges. We're going to compare it to a known series, which I'm going to call B sub n, a series that we know whether or not it converges. And there's a basic idea here in these comparisons that kind of underlies the idea behind the specifics of the direct comparison test and also the specifics of the limit comparison test, which we will look at in the next video. And so I want to start with that foundational idea. We're going to say that both of our series here, A sub n, the series of interest, and B sub n, the known series, these are both series of positive terms. Eventually, could be that the first couple terms are negative, but eventually these are positive terms. And for our first discussion, I'm going to say that B sub n is a series that we know converges. We know that this series converges. So let's think about what that means. It means that the terms of this series approach zero, and it means that they approach zero quickly. So let's say that maybe my terms here look something like this. They approach zero and they approach zero quickly. Well, let's imagine that my A sub n series, that all of these terms happen to be smaller than the terms of the known series. So my A sub n series looks like this. And hopefully the idea here makes sense that if this series is always smaller than the B sub n series, which we know converges, if A sub n is smaller, then it has to converge as well. If for all n eventually, could be the first few terms of the series are a little weird, but for all n eventually, if A sub n is less than B sub n, if my series of interest is smaller than this series that I know converges, then A sub n, oh, sorry, I should write that as then the series also converges. Now, if we have a known series B sub n that converges and A sub n happens to be larger than B sub n, then hopefully it makes sense that we don't know then if A sub n would converge or not. If A sub n is greater than B sub n, maybe it approaches zero fast enough to converge, but maybe it doesn't, or maybe it just increases. We don't know. But if B sub n converges, and if all the terms of A sub n are smaller than the terms of B sub n, then it would have to converge as well. Now let's consider kind of the opposite of that. Let's imagine that our known series B sub n diverges. So I have a series of interest A sub n, and I have a known series B sub n that diverges. So if a series diverges, that could mean several things. It could mean that the terms are increasing, which in that case, they're not approaching zero, and we would just say it diverges by the nth term test. But for this example, for this discussion, I'm going to say that this B sub n series, which is diverging, I'm going to say that those terms are still approaching zero and they're decreasing to zero, but they're doing it too slowly. And that's the reason that it diverges, is that we can have terms that approach zero, but if they do so too slowly, then the infinite series is going to diverge. In this case, if my A sub n, if the terms of my A sub n series are greater than this series, So maybe they look something like this. Well, if the B sub n series approaches 0 too slowly, this series that's greater than that also approaches 0 too slowly. In fact, even slower than our B sub n series because it's greater. It's further away from 0. And so in this case, we would say if for all n eventually, A sub n is greater than B sub n, then our infinite series A sub n also diverges. And just like I said on the previous example, if in this case, if B sub n diverges and A sub n happened to be smaller than that, well, then we don't know for sure if it diverges or converges. If it's smaller, it could approach 0 fast enough to converge, or it might still approach too slowly. There's no way for us to know. But if B sub n diverges, if it approaches 0 too slowly, and my series of interest A sub n, all the terms are greater than that, then it has to diverge as well. So that's the basic idea behind the comparison tests. Let's go ahead and talk more specifically about what the direct comparison test says. So for the direct comparison test, we have our series of interest A sub n. And what we're going to do is we're going to choose a comparison series. And I'm going to call that comparison B sub n, known to converge or diverge. So we're going to pick a series that we can easily know if it converges or diverges. Most often it's a P series, sometimes a geometric series, something that we easily know if it converges or diverges. Here's what direct comparison says. If our comparison series B sub n converges, that means that the terms of that series approach 0 quickly, and A sub n is smaller than B sub n. So if B sub n is converging and A sub n is smaller than that, that means that it's also going to approach 0 even faster than B sub n because it's closer. Then A sub n also converges. And then the other possibility is that if B sub n diverges, in this case, maybe the terms are not approaching 0 or they are approaching 0 but too slowly, then if A sub n, if the terms of A sub n are greater than B sub n, which means it's further away from 0, it's approaching 0 even more slowly, then A sub n also diverges. And so that's our direct comparison series. Let's look at a couple examples. Let's say that we have 1 over the square root of n minus 2. And I'm going to have my n for this one. I'm going to start my n counting at 3 because the terms of this series would be undefined if n is equal to 2. So we're just going to start past 2 so we don't have that little issue to worry about. So I have this series, and we want to know if it converges or diverges. And you can see that it's very close to a P series. The problem is that little minus 2 there. The minus 2 kind of throws it off from being a P series. So what we're going to do is we're going to choose a series to compare to. And I'm going to choose the P series that I wish this was. Like if the minus 2 wasn't there, then I would have 1 over the square root of n. Or you could also think about that as 1 over n to the 1/2. And so this is a p series. P is equal to 1/2, which is less than 1. And therefore, we know that this series diverges. And so now that I've established that this diverges, now I want to compare the terms of the two series and see if this series is greater than or less than this one. Now remember, if my known series is diverging, I hope that my series of interest is greater than this one, because if it's greater, then I know it also diverges. So let's compare. 1 over square root of n minus 2 and 1 over square root of n. So if I think about those two terms, this one, the series of interest, that has a smaller denominator because I'm subtracting 2. And so if my denominator is smaller, that tells me that the fraction is larger. Again, if the denominator is smaller, the whole fraction is bigger. And so that means that my series of interest is greater than the known series, which diverges. And therefore, since this one is bigger, it is going to diverge as well. Therefore, also diverges. Okay, let's look at this example. A lot of times when the terms of a series involve a natural log, sometimes we can get a comparison test to work to help us figure out if this series converges or diverges. And the idea here to choose the comparison series is that we're going to think about natural log of n as being smaller than just n, which of course it is. Natural log of n, remember, is the slowest growing um, of the functions, the slowest growing. So it's going to be smaller than n. And so I'm going to imagine that this expression is kind of close to n over n cubed, which would reduce to 1 over n squared. So I'm going to have 1 over n squared be my chosen series. What we're doing here is just trying to treat this like a p series and approximating natural log of n with another function that's just n to a power, in this case, n to the first power. So we're comparing to 1 over n squared. This is a p series. P is equal to 2, which is greater than 1, and therefore this series converges. So now I want to compare these two series to each other. And what I'm hoping, since this one converges, I'm hoping that this one is smaller. Because if the terms of this series are approaching 0 quickly enough, and this one is smaller, then it's going to approach even more quickly. So let's compare our series, natural log of n over n cubed, and I'm comparing to 1 over n squared, which really we want to think about that as n over n cubed, because those are the terms that I want to look at to compare. If I compare these, my denominators are the same, and my numerators, the natural log of n is always going to be smaller than n, and therefore my series of interest is smaller than my known series, which is exactly what we wanted because the known series converges. Therefore, the natural log of n over n cubed infinite series also converges. Now let's consider an example where we would use a different type of series for our known series. Let's say that I have 4 to the n over 5 to the n plus 1. You can see here that this resembles more of a geometric series, and it's really that plus 1 that's kind of ruining it for us. It's making it not exactly a geometric series. So what we're going to do is choose, oh, I should switch colors for that. Sorry, let's get a different color for the choice. We're going to choose 4 over 5 to the n, or I could also write that as 4 to the n over 5 to the n, which obviously those are the same thing. This form may be a little bit easier for our comparison. But this is a geometric series. The common ratio here is equal to 4/5, which is less than 1, and therefore this series converges. So now we want to compare the two. 4 to the n over 5 to the n plus 1, and I'm comparing to 4 to the n over 5 to the n. Now again, since my chosen series, my known series converges, I'm hoping that the other one is smaller, because if these terms approach 0 quickly, if these terms are smaller than that, they have to also approach 0 quickly. And I can see here my numerators are the same. My denominators, the series of interest has a denominator that's larger, which means the fraction is smaller. And so it is, in fact, less than the known series, and therefore our series of interest also converges. Now let me do just one last example for us. So our series of interest is 1 over n plus 3, very close to the harmonic series. And so we're going to compare, we're going to choose the harmonic series as our comparison series. And we know that the harmonic series diverges. And so when I compare, what I'm hoping is that my series of interest is greater than this one. If these terms are approaching 0 too slowly, then I want the other series to be greater than that so that it's approaching even slower, and I know that it also diverges. So let's compare. 1 over n plus 3, we're going to compare to 1 over n. I notice that the n plus 3 denominator is larger, which means the overall fraction is actually smaller. And so in this case, my series of interest, the terms are going to be smaller than my known series, which diverges. And so here, direct comparison does not work. Direct comparison does not work. But what we can do is limit comparison, and I'll show you that in the next video.